Okay, so in this video we are going to look at electrolysis, and as you can see, the word electrolysis means electricity and the lysis means split. So you're going to use electricity to split something up, and the thing that you're going to be splitting up is an ionic compound. And when you split up an ionic compound, you get a metal and a non-metal, because ionic compounds contain metals and non-metals. Okay, so you're using electricity to split up an ionic compound, and you get a metal and you get a non-metal. In order for this technique to work, because you're using electricity, the ionic compound must be able to conduct electricity, and therefore the ionic compound must either be molten or it must be aqueous. Molten can also just be written as liquid, or it can be given the state symbol L, so that's just a lowercase l in a bracket. And by molten and liquid and lowercase l, I mean that you have melted your solid to form a liquid. Okay, so that's one way of turning a solid into a liquid, is to melt it, and we use the words molten, liquid, or a lowercase l as a state symbol. The other way to turn a solid or get a solid into liquid form is to dissolve it in water. And when we're talking about dissolving in water, we use the word aqueous, or we can use the words in solution, or we can use the state symbol AQ. They all mean the same thing. They all mean that you have dissolved something, okay? You've dissolved it in water. All right, and the reason you are doing this, the reason you're going from a solid to a liquid or from a solid to a dissolved solid, is because the ionic compounds must be in liquid form, and the reason is because their ions must be free to move to conduct electricity. Okay, when you're answering that question, it's really important that you specify it's the ions that must be free to move. If you just say particle, you're not going to get the mark. If you say charged particles, you won't get the mark. If you say delocalized electrons, okay, it's wrong. Ions are the charged particles that make up ionic compounds, and they must be free to move. Remember, in your diagrams, for your particle diagrams, as a solid, the particles can only vibrate, but as a liquid, the particles can move freely. The particles must be able to move freely. The ions must be free to move in order to conduct electricity. Okay, and once you've got your ionic compound in liquid form, you've either melted it or you've dissolved it in water, you can then use electrolysis to split it up. So I've drawn a little diagram here for electrolysis, and what I've got here is my battery. And my battery has a positive end and a negative end. So if we're using electricity, we need some sort of power supply, and that's going to be a battery. I've got a positive end to my battery and a negative end. And I connect my battery to what I call electrodes, okay? And you can use different substances as electrodes. So graphite would be a common example of a substance used as an electrode. And you connect your graphite, so your thin strips of graphite, to your battery. And the graphite that you connect to the positive end of the battery becomes positive, and the graphite that you connect to the negative end of the battery becomes negative. Okay, now graphite's not the only thing that you can use as an electrode, but it's an example. And you need to know that the positive electrode over here is called an anode, and that the negative electrode over here is called a cathode. And to remember that, I always use panic. Positive is the anode, and the negative is the cathode, okay? You do need to know the difference between the two, all right? So I will then place my positive anode and my negative cathode, okay, into a beaker that contains my ionic compound, okay? My ionic compound, I'm going to say, for example, use potassium bromide as my ionic compound. And remember, your ionic compound must be in liquid form. And in this example, I'm going to say that I've melted potassium bromide. Okay, that's how I've turned it into a liquid. I have melted it. Okay, so if we look at potassium bromide, we will see that it contains potassium and it contains bromine. But because it's an ionic compound, it contains these elements as ions. And if I find potassium on my periodic table, I will see that it always forms ions with a +1 charge. Okay, it doesn't matter what potassium is bonded to. It always forms ions with a +1 charge. And bromine, over here in group 7, always forms ions with a -1 charge. Okay, so In my beaker, I've got my potassium bromide, and I've got potassium ions floating around, and I've got bromide ions flowing around. And I put in my electrodes, and I turn on my battery, and my positive electrode becomes positively charged, and then this electrode will become negatively charged. And what will happen then is that my positive potassium ions will all be attracted to that negative cathode, and my negative bromine ions will all be attracted to my positive anode. And in doing this, I have used electricity to split up my ionic compound. I now have potassium on one side, and I've got bromine on the other side. Okay, so it's using electricity to split it up into potassium on one side, bromine on the other side. Okay, potassium positively charged goes to the negative cathode. Bromine negatively charged goes to the positive anode. Okay, and if I was asked then for my product, okay, my final product is not going to be K+. My final product at the cathode is going to be potassium, okay? And we'll look at that in a second. We'll look at how to convert that K+ back to just K, but my product is going to be potassium at the cathode, and at the anode, my product is going to be bromine. Okay, so please notice here that when I wrote the name of the compound, it was bromide, but when I'm writing the name of the product, I'm writing bromine. Okay, bromine is the name of the element. It ends in INE, and it's really important that when you're writing the product, you write it exactly the same way that it appears on the periodic table, which is going to be bromine. Okay, I'm going to do exactly the same thing, but I'm going to use potassium bromide aqueous. Okay, so remember, potassium bromide is an ionic compound. It is usually solid at room temperature. If it's a solid, it doesn't conduct electricity. So I need to either melt it or dissolve it in water before I do electrolysis. This is an example of me melting it because I have the little state symbol L, so it's melted. And now I'm going to do an example. If I dissolved it in water, what will happen? Will I get the same products? Okay, so it's potassium bromide, so it still contains potassium. And I said potassium is always a +1 ion. And then I've got bromine, which is always a -1. So far, things are still the same. But this aqueous here, okay, reminds us that we have dissolved it in water. And if you've dissolved it in water, then you've got 2 extra ions present. You've got H+ and you've got OH-. These are the ions you get from water. Water is H2O, so there's your H2 and your O. So water splits up to H+ and OH-, the same ions that you would have seen when we studied the acids topic. Okay, so instead of just having 2 ions, when I melted potassium bromide, I've now got 4 ions when I dissolve potassium bromide in water. Is this going to make a difference? Okay, well, the same principles apply. Your positive ions will go to the negative cathode, but instead of just having 1 positive ion, you have now got 2. You've got K+ and you've got H+. Okay, the negative ions will go to the positive anode, but again, instead of just having 1 negative ion, you have now got 2. So the B or minus is going to go there like it always did, but now we're also going to have OH- there as well. Okay, so if you're comparing the two, when it's molten, you just had the bromine. Now that it's aqueous, you've got the bromide ions and the OH- ions at the cathode, as well as having K+, you've now got H+. Is this going to affect your actual products? The answer is yes. Okay, it will affect your products. So you'll be asked, what's the product at the cathode, or what is the product at the anode? Okay, when you are predicting the product at the cathode, you've got 2 sets of ions here at the cathode, but only 1 will form. Okay, only 1 product is going to form. And the product that will form is always the least reactive. So you have to look at potassium and look at hydrogen and ask yourself, which is the least reactive? In order to answer that question, you need to look back at your reactivity series. And you will see in your reactivity series that potassium's at the very, very top, the most reactive that we look at, and hydrogen's right down the bottom. So when you ask yourself, which is the least reactive, the answer is going to be hydrogen. Hydrogen is less reactive, so hydrogen is the product at the cathode. And I'll just find that reactivity series for you. because when I show you your activity series, you'll see that hydrogen is less reactive. So boom, here we go. So this is your reactivity series that I was talking about, okay? So potassium right at the top, hydrogen's all the way down here, and the least reactive always forms. So hydrogen is going to form. And you will see that hydrogen is less reactive than most of your metals, which means if you are using a dissolved ionic compound, then hydrogen is always going to form at the cathode. The only exception is with copper. Okay, hydrogen is more reactive than copper. So if you had copper as your metal, copper will form. Okay, the least reactive always forms. Hydrogen is less reactive than iron and zinc and calcium and potassium, which means hydrogen will form. But hydrogen is more reactive than copper. So if copper was your metal, copper would form. Remember, silver and gold generally very unreactive, and you don't need to carry out this technique on them. Okay, so hydrogen is going to form at the cathode. And then at the anode, slightly simpler, okay, at the anode, the halogen is always going to form. By halogen, I mean the element in group 7. Bromine is in group 7, so bromine is going to form, okay? So you see, exact same ionic compound, but if you melt it, you get potassium forming at the cathode, and if you dissolve it, you get hydrogen forming at the cathode. At the anode, the product is the same in both instances. I'm going to give you a few of these questions to do for yourself. Okay, so over here I've prepared some questions, and what I want you to do is look at the ionic compounds that you're given and figure out what's going to form at the cathode and what is going to form at the anode. Okay, to approach these questions, the very first thing you should do is just label your cathode and anode. So I know negative is cathode, and I know positive is the anode. So I'm going to put that above the cathode and the anode. Okay, and in this case, I haven't given you the ions. Okay, so you know that the positive ions are going to go to the cathode and the negative ions are going to go to the anode. But when I don't give you the ions, it's harder because you need to know the charges on the ions yourself. Okay, you can work this out from your periodic table. Okay, so magnesium bromide. Magnesium's in group 2, it's got a charge of +2. Bromine's in group 7, it's got a charge of -1. So I can find out all of these charges from the periodic table. But an even kind of quicker way, okay, is you're given an ionic compound. The first word of the ionic compound is always the metal. Okay, the metal is always the first word, and the non-metal is always the second word. Metals always form positive ions. Always. It could be +1, +2, +3, depending on what group they're in, but they're always going to be positive. Non-metals will always form negative ions. Okay, again, it can be -1, -2, -3, depending on the group, but they're all going to be negative. Okay, so if your metal, which is always the first word, is always forming a positive ion, then your metal, the first word, is always going to be attracted to the cathode. The non-metal, which is always the second word, is always going to be negative, so the non-metal is always going to go to the anode. So if I was doing this one, the first one for you, I know magnesium is a metal, I know it's going to be positively charged, and I know it's going to go to the cathode. Bromine, that's your non-metal, I know it's negatively charged, I know it's going to go to the anode. And just take care, again, when I'm writing that product, I'm not writing it as bromide, I'm writing it as bromine, because that's how it appears in the periodic table. Do the other 5 yourself, but take care where I have said AQ instead of L. That means you've also got H plus and OH minus present, and that could affect your answer. Press pause, do the questions, and then press play when you're ready for the answers. Okay, so answers. Sodium, okay, is your metal. It's going to become positively charged, so it's going to be attracted to the cathode. Chlorine is your non-metal. It's going to be negatively charged. It's going to be attracted to the anode. So sodium and chlorine are your answers there. I'm going to skip this one for a second and do iron. So iron is a metal. It's going to be positively charged, so it's going to go to your cathode. Iodine is a non-metal. It's going to be negatively charged. It's going to go to your anode. Copper is a metal. It's going to be positively charged. It's going to go to your cathode. Bromine is a non-metal. Negatively charged will go to your anode. Okay? I'm going to come back now and do the aqueous ones. So sodium is a metal, it will be positively charged and it will be attracted to your cathode. But when it's aqueous, you've got something else that's positively charged. You've also got hydrogen. Hydrogen and sodium will both go to the cathode, but only one of the products will form. The least reactive forms, hydrogen, is less reactive than sodium. And I'm getting that from my reactivity series. So hydrogen is going to form. Chlorine and OH minus are both negatively charged. They'll both go to the anode, but the halogen, which is the group 7, chlorine, will form. Okay? Down here at the end, copper is a metal. It's positively charged. It will go to the cathode, but so will H+. The least reactive will form. Copper is less reactive than hydrogen, so copper will still form. Again, I'm getting this from my reactivity series. And when you look at the reactivity series, you will see that copper is the only metal below hydrogen, as well as silver and gold. Okay, so all of your other metals, when they're aqueous, you're going to have hydrogen, but with copper, you will still get copper formed. And again, bromine is in group 7, it's a halogen. So even though the OH minus goes to the anode as well, bromine is going to form. And just make sure that these are all ending in INE the whole way down. Okay, I'm going to come back over here. Because, sorry, it's frozen. Because we said, you know, when you initially split up your ionic compound, you have got ions. Okay, you're splitting it up into ions. When I'm writing my product, I'm not writing K+, I'm writing potassium. I'm not writing B or minus, I'm writing bromine. So you need to be able to convert those ions back into the pure unreacted elements. You need to convert them back into atoms. I'm going to look at how we're going to do that. Okay, so I'm starting off here with K+, and these are called half equations. Okay, so I'm starting off with K+, and I need to convert that back to potassium, which is just K. Okay, I've written my product as potassium. The symbol for potassium is just K. At the moment, I've got K+. I need to make it K. That positive charge there tells me that potassium has lost 1 electron. Okay, the reason it's positively charged is because it's lost an electron. If I want to get rid of that positive charge, well then I need to give it its electron back. So K+, it's lost an electron. I give it the electron back, and then it's just K again. Okay, if I were to do that with another element, just say I had calcium instead. Calcium's in group 2 and has a 2+ charge. Okay, I want to take my calcium ion with the charge and convert it back into a neutral calcium atom. How am I going to do that? Okay, that 2+ tells me it's lost 2 electrons. So I'm going to give it the 2 electrons back again, and it will be calcium. Okay, so what you're seeing from these equations is that you're starting off with an ion. You've got something charged on the left-hand side, and you're turning it back into the neutral atom without the charge. Plus means it's lost an electron, so I'm going to give it the electron back. That means these two signs, plus, 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 they are matching. Okay, if it's lost 1 electron, I give it 1 electron back. If it's lost 2 electrons, I give it 2 electron back. If it was +3, I would give it 3 electrons back. Okay, they are your half equations. All right. And in each of these equations, you can see that you are giving the ions electrons. The ions are gaining electrons. And if you remember oil rig, you know that oxidation is loss, reduction is gain. And with oil rig, you're talking about electrons. So reduction is gain of electrons. You can see that your ions are gaining electrons each time. So I can say that this is an example of reduction. Okay, so these are the half equations that I would see at the cathode, okay, because my positive ions go to the cathode, and then at the cathode, they get their electrons back, they become neutral atoms once more. And because they're gaining electrons, I say it is reduction. All right, if I were to look at this same reaction, but look at the anode, okay, I have Br minus, okay, and I want to convert that back into normal bromine. All right, that minus tells me that bromine has gained an electron. If I want to make it neutral, then I need to take that electron away again. So it's going to be minus an electron. Okay, so we have the same situation as what we had above. You're starting off with an ion and you're ending up with something neutral. and the signs are matching. So when this is a minus ion, I'm taking the electron away. Okay, minus means gained an electron. I take that electron away and it's going to be neutral again. Okay, the thing with the halogens though is they don't exist as individual atoms. So you see I have them all circled here. They don't exist as individual atoms. Instead, the atoms pair up and they form what we call diatomic molecules. So instead of writing it as Br, I need to write it as Br2. Because I've got 2 bromines on this side, I need 2 bromines on this side, which means I need to lose 2 electrons. So I'm basically going 2, 2, 2. It'd be exactly the same if I had chlorine. Chlorine's also in group 7, so it forms a minus ion. I'd want to make my Cl minus back into Cl. It's gained an electron, so I would take an electron away. But chlorine, just like bromine, forms a diatomic molecule. So I needed 2 there, which means I needed 2 there, which means I needed 2 there. Okay? In each of these half equations, you can see that your ions are losing electrons. Oil rig, oxidation is loss. So at the anode, I can say oxidation is occurring because my ions are losing electrons. Okay? If I come over here to the other side, all right, same situation, but at the cathode, we can see that hydrogen is being formed. So if hydrogen is being formed, I've got a different half equation to write. Okay? I'm starting off with H+, and I want to turn that into H. That positive charge tells me hydrogen has lost an electron, so I'm going to give it the electron back, give hydrogen its electron back, and I'm forming a hydrogen atom. However, when I look at my periodic table, I see a hydrogen is another one of the ones I've circled. So all of the circled elements on my periodic table are the elements that occur as diatomic molecules. So that means I have to put a little 2 here, just like I did over here, which means I need a big 2 and I need a big 2. Okay, so that's my half equation for hydrogen. And again, it's gaining electrons, so I can say it's reduction. You're always going to get reduction at the cathode, oxidation at the anode. Okay, so you initially split your ionic compound into ions, but then you need to convert them back to atoms. The positive ions need to gain electrons to become atoms again, so we say they're reduced. The negative ions need to lose electrons to become atoms again. We say they are oxidized. So I want you to write me half equations for the following ions. So these are the ions you are starting with. How are you going to make them neutral atoms again? Okay, so you need to write half equations for these 5 ions, and then I want you to tell me if it's oxidation or if it's reduction. Just so you're aware, fluorine and iodine are both in group 7, so they will exist as diatomic molecules. The rest of yours will just exist as single atoms. So press pause, write me those half equations, and then press play again. Okay, so here are your half equations. Okay, the first 3 are all positively charged, which means they all need to gain electrons. Okay, so they've all originally lost electrons, so they need to gain electrons in order to become neutral. Magnesium's lost 2 electrons, so I give it back 2. Iron's lost 2, so I give it back 2. Copper's just lost 1, I give it back 1. You've got an ion on the left-hand side, you've got something neutral on the right-hand side, and these signs are matching. Because they're all gaining electron, it's always an example of reduction, and this would all take place at the cathode. The next 2, okay, you've got negatively charged ions. That means they've gained an electron, so you are going to take that electron away. Because they're both in group 7, they're both forming diatomic molecules. Okay, so you've got 2 separate fluorine ions that each lose an electron to form 2 atoms that will then pair up and form F2. Iodine's exactly the same. So you'll notice that these equations are exactly the same as the other 2 we wrote. The halogen equations are all exactly the same. And because they're all losing electrons, we say it's an example of oxidation. Okay, there's just one more thing that I need to do with you. So this is the last thing I need to do with you. And it's an example of a practical that unfortunately we didn't actually get time to do before lockdown. But we're going to go through the theory behind it now. It is quite straightforward. So it's electrolysis again. And I've drawn my diagram for electrolysis. And can I just point something out in my diagrams for electrolysis in this video, because it's slightly different from how I usually draw them. When I usually draw my little electrolysis diagrams, I never draw the battery complete. you guys all study physics, you know that your electrical circuits have to be complete. So the way I've been drawing my diagrams in this video is the way you should also be drawing them, okay, with your positive and your negative end of your battery and the whole thing connected as one circuit. Okay, remember electricity can flow through this liquid as well, so you've got a complete circuit that electricity can flow through. The way I sometimes draw them with separate positive and negative electrodes, that's not how you should be drawing it, okay? Make sure your circuit is complete when you draw these diagrams. So yeah, I've drawn my diagram, and both of my electrodes are pieces of copper. Okay, so I take a piece of copper, I connect it to the anode, I take a piece of copper, I connect it to the cathode, and we want to know what is going to happen to the anode and to the cathode. Okay, so we're going to look at the anode first. We're going to look at what will happen to the piece of copper that's connected to the anode. Okay, we remember that at the anode, oxidation occurs. Oxidation, which is a loss of electrons, occurs at the anode, which means the copper at the anode is going to lose electrons. So I'm going to write a half equation to show that. It's going to start off with copper as a neutral atom, and I'm going to show copper losing 2 electrons, because that's the number of electrons copper will typically lose. And when copper loses 2 electrons, it becomes Cu2+. Okay, so I'm starting off with my neutral copper. It loses 2 electrons and it becomes Cu2+. How did I know it was going to lose 2? Okay, it's just something I know. Copper is here on your transition elements, so it's not in a group like the others are, and copper can lose 1 electron and form Cu+, or can lose 2 electrons and form Cu2+, and in this case I'm going to show it losing 2 electrons and forming Cu2+. So that's what's going to happen to the copper at the anode. The copper at the anode starts off as neutral, it loses 2 electrons and it becomes Cu2+. Now once you have made your Cu2+ ions, what exactly is going to happen to them? Okay, you're making all of this Cu2+. So the Cu2+ is being made at the anode. And when you make that Cu2+, all of those Cu2+ ions are going to be attracted to the negative cathode. Okay, so you're starting off with neutral copper. They lose electrons at the anode because oxidation occurs, and they form Cu2+ ions. When those Cu2+ ions form, they are attracted to the negative cathode. So all of the copper will start to move from the anode to the cathode. What happens at the cathode when those Cu2+ ions arrive? Well, we know reduction occurs at the cathode, and reduction is the gain of electrons. So arriving at the cathode are all of my Cu2+ ions. And when they arrive at the cathode, my Cu2+ ions are going to gain electrons. How many are they going to gain? They're going to gain the same number that they originally lost. Okay, so because they're arriving as Cu2+, they will gain 2 electrons and they will become copper again. Okay, so this is what's happening at the anode. This is what's happening at the cathode. What would you actually see in this reaction? Well, the copper at the anode is becoming Cu2+ and moving to the cathode. And that means over the course of the experiment, your anode is going to become smaller because all of the copper is being converted to Cu2+ and then it's moving across. At the cathode, okay, you are going to see it get bigger because all of the copper that started in the anode is now moving over to the cathode. So you're going to see the anode get smaller and the cathode get bigger. So I'm going to write underneath copper. It's going to move from anode to cathode. Okay, so the anode gets smaller, the cathode gets bigger. And these half equations describe why. The anode, the copper loses the electrons, they become positive. As soon as they're positive, they're attracted to the cathode. That means all of your copper is going to end up moving from the anode to the cathode. The anode gets smaller, the cathode gets bigger. And once those Cu2+ ions arrive here at the cathode, they will be converted back into copper. Okay, so it's an experiment that we didn't get to do. We'll do it in year 11, but it is one that you need to know. Okay, this video, I'm sorry, is longer than intended. There's also some questions in your core info booklet in electrolysis. Okay, there's more questions on electrolysis than most of the other topics, just because I think it's worth practicing. The questions are on page 22 and 23, and all of the answers are underneath. I would recommend doing quite a few of those questions, especially like the half equations and the predicting the products, those kind of tricky questions. You can't just learn the answers off by heart. You need to understand the process and practice applying those processes. So I would really recommend doing those questions on page 23 of your core revision guides and then marking them using the answers below.